Okay, so get ready because today we are going back in time. We're going
Oh,
way back to the early 1900s
wow.
for a deep dive into this incredible encyclopedia
Really?
called How It Works by
Uh,
Archibald Williams.
Interesting.
And basically it explains all the everyday tech from back then,
Okay.
like steam engines, telephones, all that
Ah.
stuff that we kind of take for granted now.
Yeah.
But back then, this was cutting edge.
Absolutely.
And we've got these excerpts with these like vintage diagrams.
Cool.
It's going to be fun.
Yeah.
It's going to be like trying to explain Wi-Fi to
Right.
someone who's never even seen a computer.
I can imagine.
So, yeah.
It's a really fascinating look
Yeah.
at a world that was like just on the verge of like a technological explosion.
Exactly.
Yeah.
And I think what we're going to do is try to unpack
Okay.
like all the core principles
Yeah.
of these inventions and maybe even like uncover some surprising details.
I think there will be some surprises in there for sure.
I think so too.
Yeah.
You ready to get your engineering geek on?
Absolutely. Let's dive in.
All right, so first up,
Okay.
steam power.
All right.
The book starts with this really simple analogy.
Okay.
Like, picture a pot of water boiling over on the stove.
Okay.
You know how it like bubbles up and overflows?
Yep. Yep.
They're saying that's kind of similar to how the water circulates
Oh, okay.
in a boiler.
I see. That makes sense.
Yeah, and it's actually a pretty clever way to illustrate
Yeah.
this concept of convection,
Right.
where the heated water becomes less dense, so it rises,
Yeah.
and then it turns into steam, which drives the circulation.
Okay.
So it's like this constant cycle
Right.
of heating and rising and turning into steam.
Yeah.
Pretty cool.
It is.
Now, in like a steam locomotive,
Okay.
things get a little more complicated.
Yeah.
They've got this thing called a fire brick arch.
Oh, a fire brick
Yeah, it's in the firebox.
arch? Okay.
And I was like, what is that all about?
So what is it?
Well, it turns out it actually has like a few different purposes.
Oh, okay.
First of all, it deflects the flames.
So it's like directing them?
Yeah, exactly. Like making
Nice.
sure the heat is distributed evenly,
Yeah, okay.
for like optimal combustion.
I see.
And then it also acts as like a baffle.
A baffle.
Yeah, like preventing unburnt fuel from escaping.
Oh, so improving the efficiency.
Exactly.
Oh, that's smart.
Right.
Yeah.
So it's like this super efficient heat manager.
Right.
But those boilers,
Yeah.
talk about pressure cookers.
Oh, yeah.
I mean, there's a whole section on preventing explosions.
Really?
Like they were clearly a big concern back then.
Yeah. I mean, it makes sense if you think about it.
Yeah.
You're dealing with like incredibly high pressure.
Right.
And if something goes wrong,
Yeah.
it can be catastrophic.
They even mentioned this disastrous explosion at the Red Car Iron Works.
Red car.
Yeah. Yeah. It was pretty awful.
Wow.
Like multiple boiler explosions
Oh.
led to, a lot of people losing their lives.
That's a stark reminder of
Yeah.
like the dangers
Yeah.
of, working with these powerful forces.
For sure.
Yeah.
And it makes you realize just how carefully
Yeah.
they had to control everything.
Right.
But one of the devices that really caught my eye
Okay.
was this thing called the Gifford injector.
The Gifford injector.
Yeah, and this thing actually uses steam to
Ah.
blow more water into the boiler.
Wait, so the steam from the boiler
Yeah.
is used to put more water into
I
it.
know it sounds crazy, right?
It does.
But it somehow works.
Yeah. How does that even work?
So it uses these principles of fluid dynamics,
Okay.
and basically the high velocity steam
Right.
creates this low pressure area,
Okay.
kind of like a vacuum,
I see.
which then sucks in the water
Oh,
and gives it enough momentum
right.
to overcome the boiler pressure.
Wow. So it's like using the steam's own energy.
Exactly.
Against itself.
Yeah, it's like a physics magic trick. So we've got all this steam now.
Yeah.
How do we actually make it power the engine?
Yeah. That's the big question.
Right. So that's where the reciprocating steam engine comes in.
For reciprocating steam engine.
Yeah, and it's all about these core components.
Okay.
You got the cylinder,
Cylinder.
the piston,
Piston.
the kicking rod, the crank,
Crank.
and the flywheel.
Flywheel.
And each one of these plays a crucial role
Yeah.
in like converting that linear motion of the piston
Okay.
into rotary motion.
Which turns the wheels.
Exactly.
Okay.
So it's like the steam pushes the piston,
Right.
the piston rod turns the crank,
Yeah.
and that's what makes the wheels go round.
Yeah. Like a well choreographed dance
That's
of all
true.
these parts.
They use all these like cool terms like
yeah.
bore stroke,
Yes.
crank throw.
Crank throw.
I felt like I was learning a whole new language.
It's like the language of engines.
Yeah,
Yeah.
but they are important
Oh, they are.
for understanding like the engine's specs.
And
Yeah.
performance.
Yeah.
So
You know them.
It is.
Yeah.
Now, here's where things get really interesting.
Okay.
They talk about this concept called expansive working.
Expansive working.
Yeah. And it's not just about the steam pushing the piston,
Right.
like all the way.
Right.
They actually cut off the steam early,
Ah.
and then they let it expand.
Okay.
And it actually does more work.
Really?
With less fuel that way.
So it's like a way to make it more efficient?
Exactly.
Well, that's pretty clever.
Right.
Yeah.
So they're like squeezing every bit of power out of that steam.
They're not wasting any of it.
Yeah.
Yeah.
And then to control this whole process,
Okay.
they use a slide valve.
The slide valve.
Yeah. But it has this thing called lap.
Lap.
And the lap is basically like an extension on the valve.
Okay.
And it allows for like really precise control.
I see.
So it's like controlling when it enters and exits.
Exactly.
Right.
And that maximizes its expansive power.
Right.
Yeah.
So it's all about timing.
Exactly.
Yeah.
And then there's this thing called the speed governor.
The speed governor.
Yeah. Have you ever heard of that?
No, I don't think so.
Okay. So this is like this mechanical marvel
Okay.
that keeps the engine running
Okay.
at a constant speed.
Wow. So it's like a cruise control.
Kinda. Yeah.
Here for a steam engine.
Yeah. It's basically like a spinning shaft
Okay.
with these weighted balls.
Oh, weighted balls.
And as the speed increases,
Right.
the balls fly outward.
Okay.
And that adjusts a valve to control the steam flow.
I see. So it's like a feedback mechanism.
Yeah.
Okay.
So you're like constantly monitoring the speed
Right.
and then adjusting to keep it steady.
That's so clever.
Right. It's like they had automation figured out way back then.
Amazing.
All right. So let's move on from
Excellent.
these massive steam engines
Yeah.
to something a little more streamlined.
Okay.
Steam turbines.
Steam turbines.
Yeah. Now these things work on a totally different principle.
Oh, yeah.
So instead of like steam pushing a piston
Right.
in a closed chamber,
Okay.
it flows continuously
Oh,
through a series of blades,
I see.
kind of like a windmill,
Okay.
and that spins the turbine.
So it's using the steam's movement.
Yeah, it's using its kinetic energy,
Oh, wow.
which is the energy of motion.
Okay.
Right.
That's a pretty big difference.
It is.
Yeah.
Now, what's really cool is that this concept has been around
Oh, yeah.
for ages.
Really?
Like they mentioned Hero's steam turbine.
Hero's steam turbine.
Like, it's this ancient contraction
What?
with like a spinning ball
Okay.
and L-shaped pipes.
L-shaped pipes.
Yeah.
So what did they use it for?
Well, they were just like experimenting,
Oh.
you know? It
Oh.
wasn't like practical,
Right.
but it shows that like way back then,
Yeah.
they were already thinking about this stuff.
That's pretty amazing.
It is. And it like foreshadows modern turbine technology.
Right.
So
So cool.
pretty cool.
Yeah.
Now, they describe the de Laval turbine.
De Laval.
Yeah, which spins incredibly fast
Okay.
as the steam blasts through it.
Oh, wow.
But achieving these high speeds
Yeah.
came with a whole new set of challenges,
Like what?
like vibration control.
Oh, yeah.
I can imagine those things shaking like crazy.
I bet.
Yeah.
Yeah.
And then there's the Parsons turbine.
Parsons turbine.
Yeah, this is a more complex design
Okay.
with multiple stages
Oh.
to increase the efficiency.
Okay.
And they even mention its use
Okay.
in the Turbinia.
The turbinia.
Yeah, which was the first turbine-driven boat.
Oh, wow.
Pretty cool, right?
That is really cool. So
Then-
they were already applying this to like boats.
Yeah.
Wow.
And it was super fast.
Really?
Like way faster than any other boat at the time.
Oh, wow.
Yeah.
That's amazing.
So it really showed the potential of this technology.
Right.
Okay, so let's leave steam behind
Okay.
and jump to something a little more familiar,
All right.
the internal combustion engine.
Okay.
Now, this is where the combustion happens inside,
Right.
directly driving the piston.
Okay.
So no more external boilers and all that.
So it's more compact.
It's more efficient.
Yeah.
So
Big change.
yeah, big change.
Yeah.
And they describe this thing called the carburetor.
The carburetor.
Yeah. It's basically this ingenious device
Okay.
that mixes the petrol with air
Right.
to create the combustible mixture.
Well,
So it's like a tiny fuel chef.
yeah. Getting the recipe just right.
Exactly.
Yeah.
And they also talk about the silencer.
Oh, the silencer?
Yeah. Which makes you realize
Yeah.
how loud these engines must have been
Right. Without it.
without it. Yeah.
Yeah.
I mean, can you imagine?
I can only imagine.
Yeah.
Yeah.
So the silencer was a pretty important invention.
Definitely.
Right.
Yeah. For everyone's sanity.
Exactly.
Yeah.
So it's funny how every technological advancement
Yeah.
comes with its own set of problems to solve.
That's true.
Okay. Moving on from engines.
All right.
We enter the realm of electromagnetism.
Electromagnetism.
Yeah, and they start with the basics.
Okay.
You know, permanent magnets, like the ones on your fridge,
Right.
and then temporary magnets,
Okay.
which only work when there's an electric current.
Right.
So that's a pretty important distinction.
Yeah, it is,
Okay.
because it explains how a lot of these devices work.
Exactly.
Yeah.
And then they introduce this idea
Okay.
of lines of force.
Lines of force.
Yeah, it's basically these invisible paths
Okay.
that help you visualize
Okay.
magnetic fields.
Interesting.
Yeah, so imagine you sprinkle iron filings
Okay.
around a magnet.
Right.
They'll align
Oh,
along these lines.
I see. So it's like making the invisible visible.
Exactly.
Okay.
So it's like you can actually see the magnetic field.
That's pretty cool.
Yeah. And then they use this simple electric bell
Okay.
to illustrate how electromagnetism works in action.
All right.
So when you press the button,
Right.
the current flows through a coil,
Okay.
and that creates a temporary magnet.
Hey.
And then that magnet attracts like a metal hammer
Right.
to strike the bell.
Yeah.
And as soon as you release the button,
Okay.
the magnetism disappears.
Right.
And the hammer springs back.
So simple but effective.
Exactly.
Yeah.
But hold on.
Okay.
Things get even more complex
Right.
with induction coils.
Induction coils.
Now, these devices can actually increase the voltage
Really?
of a current.
So they're like voltage boosters?
Yeah, basically.
Wow.
And they explain this trade-off
Okay.
between voltage and current.
Right.
So higher voltage means lower current,
Okay.
but it still has enough energy
Okay.
to do the job.
So it's like transforming the energy.
Exactly.
Okay.
And they even hint at how this concept is used in those giant transformers you see
Right.
in power grids.
Oh, wow.
Yeah,
That's getting pretty advanced.
it is.
Yeah.
Okay, now get ready for this.
Okay.
Wireless telegraphy.
Wireless telegraphy.
Yeah, sending messages through the air.
Wow.
Back then, this was cutting-edge technology.
It must have seemed like magic.
Right.
Yeah.
I mean, can you imagine?
It's hard to imagine a world without it now.
Yeah.
Yeah.
So they describe these basic setups
Okay.
with transmitters and receivers,
Right.
both equipped with induction coils
Okay.
and these long aerial wires.
Aerial wires.
Yeah.
What
So-
do they do?
Well, the transmitter basically generates
About that.
these high voltage sparks,
Okay.
which create electromagnetic waves
Yeah, yeah.
that travel through space.
I see.
And then the receiver picks up those waves
Okay.
and converts them back
Right.
into audible signals.
Wow. So
That's pretty incredible.
it is.
Yeah.
Can you imagine the impact?
I can't even imagine. Of Marconi's first transatlantic transmission,
Oh, yeah.
sending a message across the ocean without cables.
That must have blown everyone's minds.
Right.
Yeah.
It was a total game changer.
Absolutely.
Speaking of connecting people,
Okay.
let's talk telephones.
Telephones.
Yeah. So this idea of converting sound waves
Right.
into electrical signals and then back again
Yeah.
is incredible.
It is.
They break it down,
Yeah.
the transmitter
Right.
with its vibrating diaphragm,
Okay.
the receiver with its electromagnet.
Right.
like-
So much going on.
I know.
Yeah.
It's like a mini science lab
Yeah.
disguised as a communication device.
I love it.
Right.
Yeah.
And they also mention submarine telephony.
Submarine telephony.
Yeah, which apparently had its own
Okay.
challenges compared to regular telephone lines.
Like what kind of challenges?
Well, they had to deal with like signal attenuation
Okay.
and distortion
Right.
over those long distances
Mhm.
underwater.
Oh, yeah. That makes sense.
Right, so they had to
Yeah.
develop
Yeah.
specialized cables
Okay.
and amplifiers and stuff.
I see.
It's pretty amazing
Yeah.
how they figured all that out.
Yeah. A lot of problem solving. Yeah.
Okay,
Well,
we're back to those magnets and coils again. But this time we're talking dynamos.
Dynamos.
Yeah, these are like the precursors to
Okay.
modern
I
generators.
see.
Right.
So how do they work?
Well, it's all about a coil
Okay.
rotating within a magnetic field,
Right.
and that induces an electric current.
Oh,
It's actually a pretty simple concept,
yeah.
but the implications are huge.
Right. Because now you can generate electricity.
Exactly.
Wow.
And they describe all these different types of dynamos,
Yeah.
some with multiple coils,
Right.
and these things called commutators.
Commutators.
Yeah, have you ever heard of those?
I don't think so.
Okay, so the commutator basically makes sure
Okay.
that the current flows
Yeah.
in a single direction,
I see.
which is called direct current,
A direct current.
or DC.
DC.
Yeah, and that was super important
Okay.
for powering a lot of those early electrical devices.
Right.
And then they briefly mention
Okay.
AC dynamos,
AC dynamo.
where the current flow reverses direction
Okay.
periodically.
So alternating current.
Exactly.
Okay.
Or
Okay.
AAC.
AC.
It's fascinating how they were already
Yeah.
exploring all these different ways to
Right.
generate and control electricity.
It's amazing.
It is.
Yeah.
Okay, from those powerful currents.
Right.
Let's shift to something
Okay.
a bit more delicate.
Okay.
The light bulb.
The light bulb.
Yeah.
Such a simple invention,
Right.
but so impactful.
I know.
Yeah.
So they start with the basics
Ah.
of incandescent lighting,
Right.
basically passing a current
Okay.
through a thin filament
Right.
until it glows white hot.
Yeah.
And finding the right material for that filament,
Yeah.
like a big challenge.
I can imagine
Yeah.
it has to be able to withstand
Yeah,
those high temperatures.
exactly.
Yeah.
They talk about early filaments
Okay.
made from carbonized materials.
Really?
Yeah, like cotton
Platinum?
or bamboo.
Bamboo.
And they had to put them inside a vacuum
Oh, in a vacuum.
in a glass bulb
Okay.
to prevent them from oxidizing.
Right.
It's pretty amazing how they figured all that out.
It is.
And then there are arc lamps,
Arc lamps.
which are even brighter.
Okay.
It's like a miniature lightning bolt.
Wow.
Yeah, illuminating the streets.
So how do those work?
Well, they create this this bright arc of electricity
Okay.
that jumps between two carbon rods.
So it's a different principle.
Totally different.
Wow.
Yeah.
That's cool.
Okay, let's shift gears again
All right.
and explore the world of light and lenses.
Billion lenses.
Yeah.
Okay.
So they start with this basic principle
Okay.
that light travels
Yeah.
in straight lines, but it can be reflected or refracted.
Refracted.
Yeah, which means bent.
Oh.
But it passes through different materials.
Right, like when you put a straw in water
Exactly.
and it looks like it's bent.
Yeah.
Yeah.
So they describe a convex lens,
A convex lens.
like a magnifying glass,
Okay.
which can focus sunlight
Yeah.
into this tiny, powerful spot.
Right.
Remember those childhood experiments?
Oh, yeah.
Burning things with a magnifying glass?
I do.
So that's basically the lens
Yeah.
converging those parallel rays of light
Right.
to a single point.
Which is called the focal point.
Exactly.
Very cool.
So it's pretty amazing
Yeah.
how this simple tool
Yeah.
can harness the power of the sun.
Definitely.
And then they talk about this thing
Okay.
called the camera obscura.
Camera obscura.
You've heard of that?
I think so, but remind me.
Okay, so it's basically a dox
Okay.
with a tiny hole,
Okay.
and it projects an upside-down image
Oh, yeah.
onto the opposite wall,
Right, like a pinhole camera?
exactly like the ancestor of the modern camera.
Wow.
Pretty cool.
That is really cool.
Right.
Yeah.
But instead of a tiny pinhole,
Yeah.
we can use a lens
Right.
to gather more light
Okay.
and create a brighter, sharper image.
Makes sense.
Yeah. And that brings us to the concept of focus,
Focus.
which is basically the distance
That's
between the lens
Right.
and where the light rays converge
Okay.
to form that clear image.
I see.
Right. And they
Yeah.
explain how the distance between the object
Okay.
and the lens
Right.
affects the image's location and size.
So that's why we adjust the focus on cameras.
Exactly.
Have to-
To get those like perfect shots.
That makes sense.
Okay. You ready for this?
I think so.
We're entering the world
Okay.
of microscopes and telescopes.
Wow.
Yeah.
Okay.
So it all starts with the simple microscope.
The simple microscope.
Yeah, which is basically a
Ah.
magnifying glass.
Right.
And it enlarges the image on our retina,
Okay.
letting us see all those tiny details
I see.
that
Yeah.
we normally miss.
That's cool.
Right.
Yeah.
And then they explain how this simple microscope
Yeah.
can actually be used
Right.
as the eyepiece in a telescope.
Really?
I know.
So cool.
Right.
Yeah.
And telescopes, of course, use lenses
Right.
to magnify distant objects.
Yeah, bringing the stars closer.
Exactly.
Wow.
They talk about all these different types of telescopes,
Okay.
like terrestrial telescopes,
Okay.
which have the lenses arranged
Right.
to produce an upright image.
Okay.
And then Galilean telescopes,
Oh, Lillian.
yeah, which use a concave lens
Okay.
to create an upright image,
All right.
but in a shorter tube.
I see.
So there were all these different designs back
Yeah.
then.
Different ways to achieve the same goal.
Yeah. And then there's the prismatic telescope,
Prismatic.
like those fancy binoculars,
Okay.
which use prisms to fold the light path.
Okay.
So they're more compact.
Oh, that's clever.
Right.
Yeah.
And then they briefly introduce
Okay.
the reflecting telescope,
So reflecting telescope.
which uses a mirror
Oh.
instead of lenses
I see.
to gather light.
Okay.
And then back to the microscopic realm,
Okay.
we have the compound microscope.
Compound.
Yeah. This one combines
Okay.
two lenses,
All right.
an objective lens
Okay.
and an eyepiece
Well, I see.
to achieve those super high levels
Right.
of magnification.
Yeah, so you can
Yeah.
see like the really tiny stuff.
Exactly.
Yeah.
And it's mind-blowing how we can see these tiny worlds
It is.
thanks to this clever combination of lenses.
Yeah, lenses are amazing.
They are.
Yeah.
And it's fascinating how these same principles
Yeah.
behind telescopes and microscopes
Right.
were used in the magic lantern,
The magic lantern.
which was basically an early projector.
Oh, wow. Wow. So cool. Right. Okay, now let's tune in to the world of sound and music.
Sound and music.
Yeah.
Okay.
So they start by talking about the human ear. Oh, the human ear.
And it's amazing design.
Yeah, it is pretty amazing.
I know.
Yeah.
So the eardrum vibrates.
Right.
And then those tiny bones in the middle ear.
Yeah, the ossicles.
Yeah,
They amplify those vibrations.
exactly.
Yeah.
And then those vibrations reach the cochlea in the inner ear,
Right.
which has all these tiny hair cells
Yeah.
that convert those vibrations into electrical signals.
It's like a mini orchestra in there.
It is. It's pretty amazing.
It is.
So they make this distinction between musical sounds,
Okay.
which have those regular repeating patterns of vibrations,
Right?
and then noise, which is more random.
Okay, so like a structured sound versus like a chaotic sound.
Exactly.
I see.
And then they talk about resonance.
Resonance.
Yeah.
Okay.
Have you ever heard of that?
I think so, but remind me.
Okay, so it's where an object vibrates
Okay.
more strongly
Okay.
when it's exposed to sound waves
Right.
that match its natural frequency. So they use the example of a vibrating string.
Okay.
Like if you pluck it in the air,
Yeah.
it sounds pretty weak.
Right.
But if you attach it to a larger surface,
Okay.
like a soundboard,
Okay.
that surface vibrates along with the string
Okay.
and amplifies the sound.
So it's like transferring the energy
Ex-
to a larger area.
Yeah, and that's how instruments like violins and guitars
Oh, that makes sense.
work.
Yeah.
So,
Oh,
pretty cool.
yeah.
And speaking of violins,
Yeah.
they go into their construction
Okay.
talking about how that hollow wooden body,
Right.
the soundboard,
Yeah.
acts as like a resonator,
I see.
amplifying the sound.
That's so cool.
Right.
Yeah.
And then they move on to the piano.
The piano.
Yeah, which is another like
Yeah.
marvel of engineering.
It is a complex instrument.
Oh, it is.
Yeah.
It has this massive frame
Okay.
supporting all those tightly stretched strings.
Oh, right. Yeah.
And that big soundboard
Yeah.
to create all those like rich tones.
I love the sound of a piano.
Me too.
Yeah.
It's so versatile.
It is.
Did you know the total tension on those strings
No.
can be up to 30 tons?
Wow, that's incredible.
I know, it's crazy.
Yeah.
And they explain how they use different thicknesses of wire
Oh.
for the strings
Okay.
to create those different pitches.
So that's how they make the high notes and the low notes.
Yeah, so the bass strings are thicker
Okay.
and under higher tension
Right.
than the treble strings
I see.
and the lowest bass strings.
Yeah.
They're even wrapped with copper wire
Really?
to add weight.
So it's like fine-tuning those vibrations.
Exactly.
Wow.
So it's all about like manipulating those materials
Yeah.
to get the sound you want.
That's really cool.
So we've got vibrating strings.
Right.
But what about wind instruments?
Wind instruments.
Yeah. So they create sound
Yeah.
using vibrating columns of air.
I see. Right.
So it's a different approach.
Totally different.
Yeah.
And they explain how the length
Of the air column
right.
determines the pitch.
So a longer column means a lower note,
Exactly.
and a shorter column means a higher note.
Yep. Yeah.
Okay, that makes sense.
It's like if you glow across the top of a bottle,
Right.
you can change the pitch by changing how much air is inside.
Oh, yeah, I've done that before.
Right.
That's a fun experiment.
It is.
Yeah.
And then they talk about harmonics.
Harmonics.
Yeah.
Okay.
Have you ever heard of those?
Maybe, but I'm not sure.
So it's basically those multiples of the fundamental frequency
Right.
that add like richness and complexity to the sound.
So it's like the overtones.
Exactly.
Okay.
And that's what gives each instrument its unique character.
Oh, I see.
Right.
That makes sense.
And then they delve into the organ.
The organ.
Yeah. The king of wind instrument.
Oh, yeah.
With all of its pipes and valves and bellows.
So it's like a giant breathing instrument.
It is.
Yeah.
And they even talk about different types of organ pipes.
Oh, really?
Yeah, like flute pipes,
Yeah. Flute pipes.
which work like blowing across a bottle.
Okay.
And then reed pipes,
Reed pipes.
which have vibrating reeds.
Oh, wow.
And get this,
What?
they discuss electric and pneumatic actions
Really?
in modern organs.
Wow.
So like pressing a key
yeah.
doesn't directly open a valve.
Okay.
It triggers an electrical or pneumatic system.
Wow. So it's like a hybrid.
Yeah.
That's amazing.
Right.
Yeah.
So it's pretty amazing how technology has enhanced
Yeah.
these traditional instruments.
It is.
Okay, so from creating sound,
All right.
let's move to capturing them.
Okay.
We're entering the world of early sound recording devices.
Sound recording.
Yeah.
Cool.
And it all started with the phonograph,
The phonograph.
invented by Edison.
Right.
So they describe how a needle
Okay.
carves a groove
Right.
representing those sound waves
Yeah.
onto a rotating cylinder.
Okay.
So it's like literally etching the sound.
That's incredible.
Right.
Yeah.
And then a reproducer uses another needle
Right.
to trace that groove,
Yeah.
vibrating a diaphragm.
Okay.
And that recreates the original sound.
Wow. So it's like playing back those vibrations.
Exactly.
That's so clever.
It is.
Yeah.
It's mind-blowing how they figured that out.
It is.
And then they briefly mentioned the gramophone,
The gramophone.
which used a flat disc
Oh, okay.
instead of a cylinder.
Right.
But the basic principle is the same.
Okay.
You know, a needle dancing in a groove
Yeah.
to bring those sounds back to life.
That's so cool.
Okay, so we're changing gears again.
Right.
This time to the skies above.
Okay.
We're talking about air pressure.
Air pressure.
Yeah.
Oh,
And
yeah.
how it shapes our weather patterns.
Right.
And it all starts with this simple fact
Okay.
that warm air can hold more moisture
Right.
than cold air.
That's why it rains.
Exactly.
Yeah.
So to measure this atmospheric pressure,
Okay.
they introduced the barometer.
The barometer.
Yeah, this ingenious device that can tell us whether to expect sunshine or storms.
Oh, wow. So it's like a weather predictor.
It is.
Cool.
And they describe different types of barometers,
Okay.
like the classic mercury column barometer
Okay.
and then the aneroid barometer.
Aneroid.
Yeah.
What's that one?
It uses a flexible, sealed chamber,
Oh,
so it can sense those changes in pressure.
I see.
And they explain how reading a barometer
Okay.
can help predict the weather.
Right.
So
Okay.
generally, rising pressure means fair weather,
Okay.
and falling pressure
Yeah.
means storms are coming.
So it's like a warning system.
It is.
That's pretty cool.
Right.
Yeah.
But they do emphasize
Yeah.
that weather patterns can vary
Right.
based on location.
So it's not foolproof.
It's not foolproof, no.
Yeah.
But it gives you a general idea.
Right.
All right, so we can predict the weather.
Yeah.
But what about putting that air pressure to work?
Putting it to work.
Yeah.
Okay.
They go into all sorts of applications.
Like what?
Well, one classic example is the diving bell.
Diving bell.
Yeah, have you ever heard of that?
I think so, but remind me.
Okay, so it's basically this giant upside-down chamber
Okay.
that they lowered into the water,
Okay.
and it trapped air inside.
I see.
So the deeper it went, the more the air was compressed,
Right.
but it allowed divers
Makes
to
it seem
stay underwater longer.
So it's like a portable air pocket.
Exactly.
Wow.
And then they talk about the diving dress.
It's a diving dress.
Yeah, which was like a personal diving bell,
Oh, wow.
providing a constant supply of fresh air
Okay.
to the diver.
That's pretty important.
Right.
Yeah.
Can you imagine the pressure
Oh, yeah.
those divers must have experienced?
That must have been intense.
Yeah.
Yeah.
And they mention how they used compressed air
Okay.
to power tools underwater.
Really?
Yeah. So it's like they brought the workshop
Wow.
down to the seafloor
That's amazing.
and back on land.
Okay.
We have the invention of pneumatic tires.
Oh, pneumatic tires.
Yeah.
Yeah.
It's hard to imagine those bumpy rides
Oh, yeah.
in horse-drawn carriages before this.
Right. So,
Big improvement.
big improvement. And
Yeah.
then they talk about air guns,
Air guns.
which use compressed air
Right.
to fire projectiles.
Okay.
So it's fascinating how they harnessed
Yeah.
that pressure
Right.
to create a force.
That's pretty clever.
And even something as simple as a self-closing doorstop
Oh, yeah.
uses air pressure.
Really?
I know.
I never thought about that.
It's so amazing how it's everywhere.
It is.
Yeah.
It's like this invisible
Yeah.
force
Right.
that's all around us.
Yeah.
Okay, so we've explored all these specific applications,
Yeah.
but now let's zoom out
Okay.
and look at the bigger picture,
All right.
those fundamental principles that govern
Okay.
how things move.
So the laws of motion.
Exactly.
Yeah.
And it all starts with forces.
Forces. Okay.
So they introduced this concept
Okay.
called force resolution,
Force resolution.
where a force acting at an angle
Okay.
can be broken down into two
Uh,
components,
Okay.
horizontal and vertical.
I see.
So it's like dissecting the force
Yeah.
to see how it's pulling in
Right.
different directions.
Okay.
And they use the example of a kite
A kite.
flying in the wind.
Okay.
So the wind's force has a lifting component
Right.
pushing the kite up,
Yeah.
and then a dragging component
Okay.
pulling it horizontally.
I see.
And they connect this principle to sailing.
Sailing.
Yeah.
Okay.
It's mind-blowing how sailboats
Right.
can actually move against the wind
Yeah.
by harnessing those resolved forces.
That's always seemed like magic to me.
I know.
Oh.
Okay, from kites and sailboats,
All right.
let's float over to balloons.
Balloon.
Those giant bags of hot air
Yeah.
that defy gravity.
I love balloons.
Me too.
Yeah.
So the hot air inside,
Right.
being lighter than the surrounding air,
Yeah.
creates lift.
Okay, so it's all about buoyancy.
Exactly. And they break down all the components. You know, the envelope that holds the air, the basket, the burner, and the ballast, which you can release to control altitude.
Oh, that's cool.
It's amazing how they control these gentle giants of the sky.
It is amazing.
Then they introduce airplanes, which are obviously much heavier than air,
Right.
but they fly
Yeah.
because their wings generate lift.
So it's a different principle.
Totally different.
Yeah.
It's all about aerodynamics.
Aerodynamics. Yeah.
So the shape and angle of the wings, combined with their forward motion, create this pressure difference that lifts them off the ground.
That's pretty amazing.
And they talk about control surfaces,
Control surface.
like the ailerons, the rudder, and the elevator, which allow the pilot to steer and maneuver the plane.
So it's all about controlling that lift.
Exactly.
That's really cool.
Okay, let's bring things back down to earth.
Right.
Literally.
Okay.
And explore the world of pumps.
Pumps.
Yeah.
Okay.
So they're all about moving fluids, right?
Moving fluids.
Yeah.
Yeah, that's their job.
And they start with the basic principle of a suction pump.
A suction pump.
Which creates a vacuum that draws fluid into a chamber.
Okay.
Think about using a syringe
Oh, yeah.
to draw liquid.
Right.
That's the basic idea.
I see.
And they describe different types of pumps,
Okay.
like the bucket pump,
A bucket pump.
which uses a bucket with a valve
Okay.
to lift water from a well.
So it's like a manual pump.
Yeah.
Okay.
And then there's the force pump,
The force pump.
which uses a piston to create pressure
Okay.
and push the water
Okay.
to even greater heights.
So it's more powerful.
Yeah. And they even mention using an air chamber in a force pump to smooth out the flow and prevent damage to the pipes.
So it's like a shock absorber.
Exactly.
For the water.
It's amazing how they refine these designs
Yeah.
to be more efficient and durable.
They were really thinking about it.
Okay. Are you ready for this connection?
I think so. What is it?
They compare pumps to the human heart.
The human heart.
Yeah.
Wow.
So the heart is basically a pump.
Right. It pumps blood
It pumps blood.
throughout the body.
Exactly.
Yeah.
And they describe the heart's 4 chambers,
Okay.
those atria and ventricles, and those crucial valves.
Yeah.
They keep the blood flowing
Yeah.
in the right direction.
They're essential.
They are.
Yeah.
It's all perfectly orchestrated
It is.
to keep us alive.
The human body's amazing.
It is.
Yeah.
And they explain the difference between arteries,
Okay.
which carry that oxygen-rich blood
Right.
away from the heart,
Yeah.
and then veins,
Veins.
which bring the oxygen-depleted blood back to the heart.
So it's like a loop.
Yeah, it's like a complex network
Yeah.
of highways and byways,
That's a good analogy.
transporting all this essential supplies
Right.
throughout the body.
So cool.
And then those tiny capillaries,
Capillaries.
the smallest blood vessels,
Okay.
that's where the real magic happens.
What happens there?
So they're so thin
Okay.
that oxygen and nutrients can pass
Oh,
through their walls,
I see.
nourishing our tissues,
Okay.
and waste products can be removed.
So it's like a microscopic delivery service.
Exactly.
Wow, that's incredible.
Pretty amazing.
Yeah.
And we can't forget the lungs,
A lung.
our body's oxygen factories.
Right.
So as blood flows through the lungs,
Yeah.
it picks up fresh oxygen
Okay.
and releases carbon dioxide.
Right. So it gets refreshed.
Exactly.
Okay.
Keeping our blood clean
Yeah.
and oxygenated.
Essential.
Essential. So we've got this incredible pump
Yeah.
circulating blood.
Right.
But what about the water
Water.
that keeps us going?
Right.
How do we get clean water
Yeah.
to our homes?
That is a good question.
They start with the sources,
Okay.
wells,
Yeah.
which tap into those underground aquifers,
Right.
and then rivers,
Rivers.
which provide surface water.
Okay.
So different sources.
Yeah. Different challenges.
Yeah, different
I
challenges.
remember getting clean water.
And they talk about the importance of water treatment,
Water treatment.
especially for that river water,
Right.
which can be full of impurities.
Yeah. You need to get rid of all that stuff.
Exactly.
Yeah.
So they describe a water treatment plant
Okay.
with its settling tanks,
Right.
its filters,
Filter.
and its disinfection processes.
Disinfection.
Yeah.
Important.
It's amazing how they can turn
Yeah.
like murky river water
Right.
into something we can safely drink.
It is amazing.
And they mention household water filters.
Oh, yeah.
Like those with porous ceramic candles
Okay.
that trap those contaminants.
Right. Like an extra layer of protection.
Exactly.
Okay.
All right, so we've got clean water
Yeah.
flowing into our homes.
Right.
But how about harnessing the power of water itself?
The power of water.
Yeah.
Okay.
They talk about water wheels.
Water wheels.
Yeah, those ancient devices
Okay.
that use the force of flowing water
Right.
to turn a wheel.
Okay.
And then they introduced the Pelton wheel.
The Pelton wheel.
Yeah, which is a more modern type of water turbine.
Okay.
That uses these high-pressure jets of water.
Oh, wow.
To spin a wheel.
So it's like a water-powered engine?
Yeah, basically.
That's cool.
And they compare it to the massive Laxey wheel.
Laxey wheel.
On the Isle of Man.
Okay.
Which was used to pump water.
Oh, wow.
Out of a mine.
So it was a huge wheel.
It was a huge wheel.
Wow.
It's a fascinating contrast.
Yeah.
Showing how water-powered technology has evolved.
Way over time.
Okay, are you ready for a little spin?
A spin?
Yeah.
Okay.
We're diving into the world of centrifugal force.
Centrifugal force.
Yeah. So it's basically that outward force that you feel when something's spinning.
Like on a merry-go-round.
Exactly.
Good.
And they use the example of a cream separator.
A cream separator.
Which spins milk at high speed.
Okay.
Separating the denser cream from the lighter milk.
So it's using that force to separate things.
Exactly.
Yeah.
And they talk about the hydro extractor.
Extractor.
Which uses the same principle.
Okay.
To spin water out of clothes.
Oh, yeah.
In a laundry setting.
Like a high-speed spin cycle.
Exactly.
Okay, that makes sense.
It's pretty cool.
Pretty cool.
Yeah.
Okay, from spinning clothes to something a bit more comfortable.
Okay.
Hot water system.
Hot water systems.
Yeah.
So
those marvels of modern plumbing.
Yeah.
Keep us warm and clean.
I love a hot shower. Me too.
Yeah.
So they discuss two main types.
Okay.
Tank systems.
Okay.
And cylinder systems.
Cylinder systems.
So the tank systems is like the classic setup.
Right.
With the tank above the boiler.
Okay.
So the heated water rises naturally to the tank.
Yeah.
And it's stored there until you need it.
So it's all that convection.
Exactly.
Right.
That hot water being less dense rises up.
Okay.
Then you have the cylinder system.
The cylinder system.
Which has a cylinder near the boiler.
Okay.
How's that different?
So how does that work?
Well, in the cylinder system, the heated water from the boiler actually circulates through a coil inside the cylinder.
I see.
So it's heating the water more directly.
Oh, so it's more efficient.
Exactly.
Oh, yes.
And it provides a more consistent supply of hot water.
That's good.
Yeah.
Yeah.
All right, so we've got our hot water on demand.
Right.
But where does that heat come from?
Yeah.
In the first place?
Good question.
That leads us to the fascinating world.
Oh.
Of combustion.
Combustion.
Yeah.
Okay.
It's all about fire.
Fire. Huh.
Yeah.
All right.
So they break it down to the basics.
Okay.
It's a rapid reaction
between
a fuel like wood or gas and an oxidant which is usually oxygen.
Right.
So it's like a chemical tango.
Yeah, things are getting hot.
Yeah, things are getting hot.
Oh, yeah.
And they use the example of a lamp chimney.
A lamp chimney?
Yeah.
Okay.
To explain how it all works.
All right, so what's the chimney doing?
So the chimney creates a draft.
Okay.
Drawing in fresh air.
Right.
Providing a steady supply of oxygen to the flame.
So it's like a built-in ventilation system.
Exactly.
For the fire.
And they connect this principle to the blower plate.
The blower plate?
In a fireplace.
Okay.
Which also helps draw air. Through the fire.
Yeah, keep that oxygen coming.
Exactly.
Yeah.
So from lamps to fireplaces.
Yeah.
It's all about controlling that flow of air.
Okay.
To get the most out of the fire.
That makes sense.
You know, what about gas?
Gas.
Yeah, another fuel source that's played a big role.
Definitely.
They describe the process of gas production.
Okay.
From coal.
Coal.
Yeah, they heat it.
Right.
In this thing called a retort.
A retort?
To drive off those volatile gases.
Okay, so it's like baking out the gas?
Yeah, basically.
Wow.
And then they talk about how the gas is cooled and purified. Removing all those unwanted byproducts. Like tar and ammonia.
You don't want those.
You don't want those.
No.
So it's interesting to think about how gaslighting was a major innovation.
Yeah, it was.
Illuminating our streets and our homes. Before electric lights took over.
It's hard to imagine now.
It is.
Yeah.
And they describe incandescent gaslighting.
Incandescent gaslighting.
Which used a mantle. That glowed brightly when it was heated by a gas flame.
So it's like a different kind of light bulb.
Yeah, basically.
Okay.
Okay, so we've explored fire and light.
All right.
Now let's shift our focus to something a bit more abstract.
Abstract.
Time.
Time.
Yeah.
Wow, okay.
How do we measure this elusive concept?
Yeah, it's always moving.
I know, it's always slipping away.
Yeah.
So enter the intricate world of clocks and watches.
Clocks and watches.
Okay. And they break down a timepiece into three main elements.
Okay.
You've got the power source,
the
wheel train, and the escapement. It's like a tiny mechanical universe.
It is. I know. Many little parts working together.
I know. And they describe weight-driven clocks, like those majestic grandfather clocks.
Yeah, oh, yeah.
And then spring-driven clocks.
Spring-driven.
Yeah, which made it possible, right, to have portable timepieces.
So you could carry time with you.
Exactly.
That's cool.
And they mentioned this ingenious device called a fusee.
A fusee.
A fusee.
Yeah.
Okay.
Which was used in spring-driven clocks.
Okay.
To, like, compensate for the decreasing torque of the unwinding spring.
So it kept it accurate.
Exactly.
Okay.
That's pretty clever.
It is.
Yeah.
And then there's the escapement.
The escapement.
Yeah, this is like the heart of the timepiece.
Okay.
It controls the release of energy from the power source.
Okay.
And it regulates the speed of all those ticking wheels.
Wow.
So they describe the deadbeat escapement.
Deadbeat escapement.
In pendulum clocks.
Okay.
Where that swinging pendulum interacts with the escape wheel.
So it's all about precision.
It is.
Yeah.
And then they discuss spring balances.
Spring balances.
Which are used in watches and small clocks.
Right.
Where a tiny hairspring and a balance wheel act like a miniaturized pendulum.
I see.
So it's amazing how they managed to create these intricate mechanisms on such a small scale.
It is pretty amazing.
I know.
Yeah.
Okay, so we've got our clocks ticking.
Yeah.
Now let's move on to keeping our valuables safe.
Okay.
We're entering the world of locks and security.
Locks and security.
Yeah, so they start with those simple warded locks.
Okay.
Which had those notches.
Right.
That had to align with the key's shape.
I see.
And then they talk about tumbler locks.
Tumbler locks.
Yeah, which used multiple levers.
Okay.
That had to be raised to specific heights.
Right.
For the lock to open.
So more secure.
More secure, yeah.
Okay.
They describe the Baron lock.
Baron lock?
Yeah, which had 2 tumblers and 2 studs.
Okay.
And then the Chubb lock.
Chubb lock.
Which used multiple tumblers.
Right.
And these intricate gates.
Oh, wow.
It's like an arms race of lock design.
Yeah, trying to stay one step ahead of the lock pickers.
Okay, now let's shift gears, literally.
Okay.
And explore the world of bicycles.
Bicycles.
Yeah.
All right.
So they're all about wheels.
Right.
And these spinning things called gears.
Gears.
Yeah.
Okay.
And they explain this basic principle of gears.
Okay.
Using this simple analogy of 2 rulers.
2 rulers.
With teeth.
Okay.
That mesh together.
I see.
So if you rotate one ruler.
Yeah.
The other one rotates too, but at a different speed.
Okay.
Depending on the number of teeth.
I see.
So it's like this mechanical dance of ratios.
That's a good way to put it.
And then they explain how gears are used in bicycle hubs to create these multi-speed systems.
Multi-speed.
Yeah, so you can shift gears.
Right. Make it easier to pedal.
Exactly.
Up hills.
Make it easier to go uphill or faster on flat ground.
That's so clever.
It is.
Yeah.
And they even mention the formula for calculating gear ratios.
So you can figure out the exact speeds. Cool.
Okay, from personal transportation to something that feeds the world.
Okay.
Agricultural machinery.
Agriculture machinery.
Yeah.
Yeah.
So they focus on the threshing machine.
The threshing machine.
Which separates grain from straw.
Okay.
And they describe all those moving parts.
Yeah.
The drum, the concave, the shakers, the blowers.
Wow.
All working together.
Yeah.
To separate those precious grains.
That's pretty amazing.
Okay. We've explored all these incredible machines on land.
Yeah.
Now let's turn our attention to the vast oceans.
The oceans.
And those mysterious forces that govern the tides.
The tides.
So they explain how the moon's gravity pulls the water on Earth toward it.
Okay.
Creating a bulge on the side facing the moon.
Okay.
And then because of inertia, there's another bulge on the opposite side of the Earth.
Interesting.
And then they describe how Earth's rotation combined with the moon's orbit creates those high and low tides that we experience throughout the day.
It's like a cosmic dance.
It is.
Yeah.
And they distinguish between spring tides.
Spring tides.
Which are those extra high tides. That happen when the sun, moon, and Earth are aligned.
I see.
And then neap tides.
Neap tides.
Which are those less extreme tides.
Okay.
When the sun and moon are at right angles.
So it all depends on the alignment.
It does.
Wow, that's fascinating.
It is.
Yeah.
So we've journeyed through like a whirlwind of technological marvels.
We have.
From steam engines and turbines to internal combustion engines.
Yeah.
Electromagnetism, wireless communication telephones.
Wow.
Dynamos, electric lighting.
So much.
Optics, microscopes, telescopes.
It's mind-boggling.
Sound musical instruments.
Yeah.
Pumps the human circulatory system.
Right.
Water supply, water power, centrifugal force.
Wow.
Hot water systems, combustion, gas production, timekeeping.
That's incredible. Locks, bicycles, agricultural machinery, and even the tides.
We covered a lot of ground.
I know.
Yeah.
It's amazing to think
That is.
how much we've learned from this single book.
Yeah.
Published over a century ago.
It's a testament to, like, the power of those fundamental principles.
It is.
Yeah.
So for you listening out there, what stood out to you during this deep dive into how it works?
What really caught your attention?
Was there a particular explanation
Yeah.
that made you go, wow, I never knew that?
Or maybe sparked a new interest.
Exactly.
Yeah.
We'd love to hear your thoughts.
We would.
And here's a little thought experiment. To keep those wheels turning,
All right.
imagine you had to explain one of these technologies to someone from a completely different era.
Like someone who had never seen any of this stuff.
Exactly.
Wow.
How would you make it understandable?
Yeah.
How would you make it relatable?
That's a great challenge.
It is.
Yeah. Until next time, keep exploring, keep learning, and keep diving deep into the fascinating world of how things work.